Hello everyone, my name is Olivier. I am Product Innovation Manager for Curamik Substrates and Coolers at Rogers Power Electronics Solutions. I am pleased to have you all on board for this webinar entitled Curamik Liquid Cooling Solutions. First, I'd like to mention that this webinar will be uploaded in our Design Hub within the next few days. So you can follow the link indicated here and register into the Design Hub. You will then get full access to this webinar and other technical and product information. Let's get started with our webinar. Here is the outline for today. After a short introduction, I will first highlight the fact that semiconductor devices require thermal management. I will then provide a brief overview of the different technologies available to dissipate the heat from these devices. And finally, I will give detailed information about the structure and performance of liquid cooling solutions from Curamik before we conclude this webinar. A significant portion of the amount that flows through a semiconductor is lost in the form of heat. This is valid for all semiconductor devices, but in this webinar we will be looking at power devices like IGBT, MOSFET, high brightness LED and high power laser diodes only. These devices can deliver high output power, and even if their efficiency is getting better and better, a few % of losses still means quite a lot of waste heat. In addition, those devices and their packages are getting smaller and smaller, so heat flux density will continue to increase. If this heat is not removed, semiconductors run at high temperature, which not only lowers their efficiency but also make them less reliable. Ultimately, thermal runaway may occur and these devices will be destroyed. Different cooling solutions are available, as there is not one solution that fits all applications. In this webinar, you will get an overview of the different cooling technologies. The benefits and drawbacks of each technology will be highlighted in order to provide guidance for the selection of the best one for your application. And finally, liquid cooling technology from Curamik will be presented as a suitable solution for the most demanding applications. As already mentioned before, semiconductor devices generate heat during operation. Let's look first at IGBT power modules. Transistors are not ideal switches, and a portion of the input electrical power is lost. In the on state or conductive mode, the voltage drop between collector and emitter is not zero, and once multiplied by the collector current, we end up with significant conduction losses. Also, during switching on and off the load, current and voltage do not immediately turn on and off, but may overlap for a while. For devices with a slow switching time, this generates again significant switching losses. Of course, semiconductor technology keeps on improving and losses will be reduced in the next decades, but we can expect an increase in heat density as the size of the devices will shrink at an ever faster pace. Okay, well, semiconductor devices generate heat, but how much heat? As we speak about heat, it is important to consider the area in which that heat is generated and the surrounding space in which it can be dissipated. Large amount of heat could be removed from a hot device if the area and volume available for heat dissipation would be unlimited. Unfortunately, this is not likely to be the case in reality, and particularly not with power semiconductors, which are mounted in small packages and integrated in systems which offer only very limited space for cooling around those packages. For power semiconductor devices, heat flux density is typically in the range of 100 watt per square centimeter. Besides, when the designer is facing space constraints, as it is for example the case in automotive under the hood applications, the cooling solution will have to be very efficient to remove such a high heat density in a very compact form factor. Laser diodes generate even more heat. They transform a given electrical input power into useful optical power, and the power left behind is deposited in the device as waste heat. Figure 1 shows the optical output power and power conversion efficiency for a 1 cm laser bar mounted on a water-cooled microchannel heatsink. As indicated here, a peak power of 364 watts can be achieved while holding the water temperature at 6 degrees C. But the best power conversion efficiency is achieved for 100 watts of output power, as the performance of diode laser material degrades at higher temperature. In any case, driving a high-power diode laser bar inevitably means a large amount of heat and current is concentrated in a very small area. Take a look at the green arrows. For 100 watts of optical output power, 80 watts of waste heat is left in the diode. As the surface of the diode is 0.1 square centimeter, this means 800 watts per square centimeter. If you look now at the red arrows, for 360 watts of optical output power, 450 watts of waste heat is left in the diode. That means 4,500 watts per square centimeter. Again, laser bars generate significant heat flux density. In addition, laser bars must be stacked, and the pitch between each laser bar has to be as small as possible to achieve the best possible laser beam quality. Therefore, compact and very efficient cooling solutions are required for such applications. While this should be clear from these few examples that significant amount of heat can be generated and has to be removed, but how to dissipate that heat? So, what are the different ways to dissipate heat? 3 mechanisms for heat dissipation exist: radiation, conduction, and convection. As time is limited for this webinar, we will not speak about heat radiation. Even though heat radiation can have a significant influence in some applications, in the case of power electronics, its contribution to heat dissipation is usually less important than with heat conduction and heat convection. In all cooling applications, heat from the device heat sources must first travel via thermal conduction to the surfaces exposed to the cooling fluid before it can be rejected to the coolant. Conduction is the transfer of heat through a medium. Heat conduction, when combined with heat spreading, is meant to transfer the heat from a small area in which heat is generated to a larger surface. The larger the surface will be, the more heat will be exposed to and can be exchanged with the coolant at the same time. This is quite obvious. Also, it is common sense that heat convection depends on the temperature difference between the hot surface and the cooling fluid. But you should not note that next to the contact surface area and the temperature difference, there is an additional parameter that has a significant influence on the heat convection. This parameter is called heat transfer coefficient. Let's have a closer look at this parameter now. Heat transfer is mainly driven by the movement of fluids. Heat transfer can be classified as free, natural convection when fluid motion is caused by buoyancy forces. Buoyancy forces result from the density variations due to variations of the temperature in the fluid. When the fluid is forced to flow over the hot surface by an external source, such as fans or pumps, heat transfer is classified as forced convection. In both cases, the flow can be internal or external. Internal flow occurs when a fluid is enclosed by a solid boundary, such when flowing through a pipe or channels. An external flow occurs when a fluid extends indefinitely without encountering a solid surface. Finally, we can distinguish between laminar and turbulent flow. The latter is characterized by chaotic changes in pressure and flow velocity. It is in contrast to a laminar flow, which occurs when a fluid flows in parallel layers with no disruptions between those layers. Obviously, the best heat dissipation can be achieved by forced convection and with turbulent flow inside a structure. The heat transfer coefficient is the ratio between the heat flux and the thermodynamic driving force for the flow of heat, in our case, the temperature difference. Typical values for heat transfer coefficient vary from very few up to many thousands watt per square meter Kelvin. As was shown before, for a given medium, forced convection is always better than free convection, but higher costs are associated with the required external source for fluid movement. Liquid cooling, for instance with water, outperforms air cooling by having heat transfer coefficients several orders of magnitude higher, thus enabling much higher pore densities and more compact solutions. However, liquid cooling comes with its own risks and potential problems, such as leakage, corrosion, and condensation. Therefore, liquid cooling is reserved for applications involving pore densities that are too high for safe dissipation by air cooling. But liquid cooling has to be preferred to air cooling for application where compact and lightweight solutions are required. Examples of liquid cooling solutions include cold plates and tubes, macro and micro channel coolers. Curamik products belong to the category of micro channel coolers and are meant to be operated with pumps under forced convection conditions. We will look at these products in a more detailed manner later on. A very efficient heat transfer can also be achieved with so-called two-phase systems. Two-phase systems show a superior heat transfer coefficient because their cooling medium can absorb significant amount of heat during the phase change. The absorbed heat is then transferred and dissipated. In this slide, you can see an example of two-phase system. Heat from the hot device transforms liquid into vapor, and the vapor is returned to liquid phase when it transfers heat to the air in a air-cooled condenser. In this example, evaporator and condenser are two different units locally separated and connected with a vapor and a liquid line. Such a system may be bulky and is not well suited for applications with space constraints, like it is the case in automotive applications, for example. In a nutshell, we can summarize the different cooling technologies as shown on this slide. While free convection in the air is easy to design and not expensive, it is a very popular cooling technology, but it usually does not provide sufficient cooling performance for most of the power electronics applications. Forced air convection is the preferred cooling technology in industrial applications, and liquid cooling is mandatory when designers are facing space constraints. The automotive industry has been using liquid cooling to cool down the combustion engines for many decades already, and will easily adopt liquid cooling again to cool down power electronics in hybrid and electric vehicles. Also, as the heat flux density will continue to increase and the miniaturization trend is not expected to stop on short term, designers will need new approaches to cool down their power devices. In the next chapter, we will introduce the curamik microchannel cooler technology as a possible solution for the most demanding applications. Well, you may have never seen a microchannel cooler and you wonder how does it look like. On this slide, you can see a cross-section of a microchannel cooler with an open structure on the top side. This way, we can recognize the internal structure from the side and from the top. The internal structure was created by stacking multiple layers of copper and joining those layers with the direct copper bonding technology, as it is already used by curamik for the production of metallized ceramic substrates. Please note that this internal structure has not been machined with CNC tools. Also, other than pure copper, no additional materials have been used to join the different layers, which anyway would have a negative impact on the heat dissipation and on lifetime. In the direct copper bonding technology, pure copper sheets are first oxidized. The thin oxide layer starts to melt at the eutectic temperature, well below the melting temperature of pure copper. The melt reacts with the other copper layers, while the bulk copper material remains solid. After cooling down, the copper layers are strongly joined together. A second recrystallization will occur during the bonding process. This means that the copper grains will grow so that we can no longer recognize the interface between each of the initial individual layers in a cross-section. In this exploded view, you can recognize each individual copper layers as well as the top and bottom DBC ceramic substrates. A very specific structure has been etched in the copper sheets before these sheets have been oxidized to enable the following bonding process. On top and bottom of the stack, either pure copper sheets or DBC ceramic substrates can be used. DBC substrates are necessary when electrical isolation between semiconductor devices and cooling medium is required by the application. Mounting holes in each layer are used for a precise alignment of all layers during stacking. The stacked layers are then screwed all together during the following bonding process to avoid relative displacement in the high temperature furnace. Screws are removed after the bonding process. Once stacked and bonded all together, a structure with holes and posts connected by wings appears through the stack of material, as can be seen in this cross-sectional view. First, the posts provide a path for heat spreading and dissipation from top to bottom. They also significantly increase the contact surface with the cooling fluid. Besides, this microchannel structure enables a cooling medium to flow in between the wings and posts. In this way, we can achieve a very efficient turbulent flow and maximize the heat exchange between copper and cooling medium. The water flow through the structure is once again depicted in this cross-sectional view. Needless to mention that the structure provides an inlet and outlet for the cooling medium, usually on the bottom of the stack of material. Also, the copper sheets are tightly bonded together on left and right sides to form hermetic walls in order to avoid any leakage. In this picture, you can see an example of microchannel cooler. Here is a view from the backside. Two mounting holes have been used for the assembly of the top, bottom and inner layers. And here you can also see two fittings for water in and outlet. These fittings are optional and O-rings in dedicated pockets can be used instead. This decision will leave it up to customer during the design phase. As can be seen on this slide, design rules for both isolated and non-isolated coolers with either O-rings or fittings can be provided to customers in order to guarantee an hermetic and reliable connection with the cooling circuit. Thermal performance is for sure the most important parameter to be considered during the design phase. Many cooling structures are possible, but over the last decades, some structures have established themselves as standard and meanwhile have a proven track record on the field. First, Cool Performance and Cool Performance Plus products have been widely adopted in the laser industry in order to cool the laser diodes. In a stack height of less than 2 mm and with as few as 5 copper layers, these products achieve a very efficient cooling locally underneath the laser bar, as they enable heat flux up to 1000 watt per square centimeter. Cool Power and Cool Power Plus are general purpose coolers. Over the course of the years, an hexagonal and rectangular shape of the posts have become the most popular structures. While the rectangular shape provides the best thermal performance, the lowest pressure drop can be achieved with the hexagonal structure. A new structure called P-flow has been introduced recently for some applications where inhomogeneous cooling is a problem and temperature variations between the devices on the top surface have to be reduced. Another important parameter to consider when you design a new cooler is the direction of the water flow relative to the position of the semiconductor devices on the top. As depicted in this slide, a serial cooling from left to right is the most evident approach, but this leads to a temperature gradient between the first and last devices. This leads to an inhomogeneous cooling due to the calorimetric heating up of the coolant. A parallel cooling is a possible workaround, but it requires additional space for a smart distribution of the water from the inlet into the channels and to the outlet. As discussed in the previous slide, thermal resistance and pressure drop are two important characteristics for coolers. Both parameters are tightly linked together as they depend on the inner structure, on the water flow rate, and on the connections with the cooling circuit. As we understand that these are two important characteristics, Rogers provides support early in the design phase. Based on the boundary conditions set by the application, thermal resistance and pressure drop can be calculated and plotted as shown here for various structures and flow rate. In addition, fluid simulation can be conducted to provide more accurate results. In this example, a specific thermal resistance of 0.2 Kelvin square centimeter per watt can be achieved at a flow rate of 8 liters per minute with a standard cooling structure. With P-flow structure, specific thermal resistance values as low as 0.1 Kelvin square centimeter per watt can be achieved. To conclude, here again a quick overview of existing ceramic liquid cooling solutions. Cool Performance and Cool Performance Plus have been developed and optimized for laser diodes cooling. They come along with or without insulation layer, as electrical insulation may be required or not. If non-isolated, DI water has to be used and the electrical conductivity has to be controlled in a range of 5 to 10 microsiemens per centimeter. The maximum allowable particle size is limited to 50 micron to avoid clogging in the microchannels. Also note that the ceramic layer, which is necessary for the purpose of electrical isolation, provides an additional value to the application as it reduces the coefficient of thermal expansion of the cooler from 17 ppm per Kelvin down to 7 ppm per Kelvin, depending on material combination. This is a better match to the CT of the semiconductor device, and this helps to reduce the bow of this device. In this webinar, we have learned that semiconductor devices generate heat, and as technology evolves, much more heat is concentrated in a small area, potentially leading to thermal runaway. We know that design engineers will have to deal with heat flux from few hundreds up to many thousands of watts per square centimeter. Unfortunately, there is not one cooling solution that fits all applications. We understand that low-cost free convection and air force cooling is good enough for numerous applications, but is not suitable for the most demanding applications. Liquid and two-phase cooling solutions provide an efficient heat dissipation up to the highest heat flux densities and in a compact size. We have seen that curamik water-cooled microchannel coolers provide a high cooling rate and the ability to cope with high total heat loads. Thermal resistance as low as 0.1 Kelvin per square centimeter per watt can be achieved in optimized configuration. A detailed description of their structure was provided in this webinar. Thank you for your attention. The session is now open for questions.